Yeah, thanks for the organizers for the opportunity to speak here. Okay, I'm going to talk about the power of time. It might mean different things to you guys, and to me it also means different things. And we will definitely see that it means different things. All right, so part of this work came out already in August, and some of it is work in progress with Andreas Blommaert and a genius student, Xunyu Yao, which is also here. So if you have any very complicated questions, just go to him. Just kidding. So I start off with some, for me at least, trivial statements, but we can contemplate that at some other time. So in quantum gravity, we sum over the topologies and we include all the loop corrections around those topologies, consider all the fluctuations. And in quantum gravity, since we do this sum over topologies, usually the sum over topologies has a genus or an expansion, and you weigh the different topologies with some weight. This weight usually suppresses more complicated geometries, more complicated topologies. But as we've seen in the past few years, or I guess maybe you can argue more generally, is that the fluctuations around certain saddles can overcome the topological suppression. And in particular, this can happen when we study observables for a very long time. Now, this sort of suggests that there could be a double scaling limit where you take the time of your observable or the quantity that you're studying very large, and at the same time make the topological suppression very large, and keep the ratio fixed. Now, this is called the tau scaling limit, and in the context of JT gravity, in the past half year, I think, or maybe this Okuyama paper was already some time back, but in the past year, 3 groups worked out this limit in a precise sense in JT gravity, approaching it from different points of view. And most of these considerations focused on the spectral form factor, sort of the hallmark of sort of quantum chaos and random matrix theory. But another observable that you could also consider is a 2-point function at late times. And what I want to do today is to understand this tau scaling limit of the spectral form factor, I won't talk much about the other observables, from a Euclidean point of view. So there was this work that's already out, and I also want to present some work on how to think about it from a Lorentzian point of view. All right, so let's consider JT gravity and its matrix model dual. In that matrix model, that's a certain double-scaled matrix model, we know there's a genus expansion in a matrix model, and there's a certain parameter, e to the minus s naught, that appears, and that parameter is a genus counting parameter. And on the gravity side, that is precisely also a genus counting parameter. From the higher dimensional point of view, you can think of S naught as the extremal entropy of the higher dimensional black hole. Right. And so the tau scaling limit, very precisely, is where we take this e to the s naught and t to infinity. So I haven't told you, we're focusing on the spectral form factor. I'll, in a moment, specify it a bit more. And then we keep the ratio fixed. Now, from the matrix model point of view, so the definition of the spectral form factor is this: 2 copies of 2 traces with beta plus IT and beta minus IT, and then we average over all Hamiltonians in that ensemble. So when t becomes very large, because we have plus it and minus it, the two sums and the two eigenvalues in those two sums, they want to be very close. You give a non-zero answer, and at that point we can use random matrix universality, the fact that when the eigenvalues become close, the connected part of the row, the density 2-point function, takes this particular form. So it has this sine kernel behavior, and then there's this delta function piece as well. Now, if you plug that into that formula, then you get an expression like this. So you massage it a little bit. So this is work by Douglas, Stanford, and I think it also appeared in this paper, but I guess Douglas maybe wrote that section. So this 2-point function, the connected part, can be written in this very simple way, where this E of rho is sort of the inverse of the leading density of states of the model that you're interested in. And this is supposed to capture the entire, some part of the full genus expansion. So we just give you the leading density of states, and then you can calculate all the corrections at any higher genus. Now there are a few things to remark about this formula is that it admits an expansion in this parameter tau, which has a finite radius of convergence. And if we take the case where the density is a monotonic function of the energy, the integral here, if we expand it, we can think about it as a low energy expansion. What it also means, sort of interestingly, is that it allows to access the plateau perturbatively. And this, if you take here tau in this formula, if you take tau to infinity, you see that it plateaus to the correct value that we expect from other considerations. This is interesting because usually we would think that the plateau is associated with highly non-perturbative physics. But here we can access it just by using the genus expansion. And it's because we take that time and the topological expression to be very large that this emerges. From the gravity side, how does that expansion work, and how does that manifest itself? So from the Euclidean point of view, and we can calculate in Euclidean signature, analytically continue, and we get a series expansion like this. So this will be the leading wormhole contribution, this guy, and then this tau cube would come from a geometry like this. Right, so this matches with the previous expression that I showed. And the way to think about these powers, so there's a tiny puzzle here, is that these powers of time that you get are 2g plus 1. But if you inspect these volumes, and so if we do the JT gravity calculation, we split the surface up in a bordered Riemann surface and some other stuff. And the volume of moduli space of those bordered Riemann surface has a particular polynomial form like this, where these powers A1 and A2 are, their sum is 3g minus 1. And so after doing these integrals by gluing everything back together, you would naively land on, after analytic, you would naively expect from this expression that you would get a power t to the 3g. Now, it turns out that there's an underlying integrability structure that constrains these coefficients here. And that's just the usual KDV hierarchy that we know and love, also from the matrix model side, that constrains these Weil-Peterson volumes. And that ensures that the growth is not t to the 3g, but actually t to the 2g plus 1. And so the Euclidean calculation gives us a very interesting way of thinking about these powers of time. There's some integrability structure going on that helps you there. So I call that the power of imaginary time. But today, the rest of the talk, what I want to focus on is to find a Lorentzian interpretation for these powers of time. And I want to convey the message, the power of time is very powerful. Anyway, right. So in Lorentzian signature, the first geometry that you can think about was studied by Saad Schenker in Stanford. It's the double cone geometry. And that double cone geometry gives a leading linear power of t behavior to the spectral form factor. So it's a geometry that you can represent like this and has a metric like that, which is compact in time. Now, what I want to, in the relative origin of time on both sides gives you this power of time. What I want to propose is that for these other powers of time that we saw in this formula, you could consider geometries like this. So you take the double cone and you cut these geometries along mirroring slits, where the slits have some size and some location along this circle. And then you glue them in a particular way together to form sort of an additional handle to the double cone. Now, and these slits, they need to be mirrored for a reason that I will come to. But the endpoints of these slits are zero modes, and since this direction here is compact, they give a t-square for each handle that you add. So that results in this power t to the 2g plus 1. Now let's look at this geometry in a bit more detail. Actually, let's first look at a flat space example of that geometry. So let's consider just Minkowski flat space, and let's do this coordinate transformation. So this coordinate transformation essentially creates a double cover of the Minkowski plane. But of course, this coordinate transformation is not well defined at the origin. And what that looks like is, and so we have the double cover. So we have two copies of this UV plane, and we glue them along a branch cut that emanates from the origin, where this coordinate transformation is not well defined. And so when we glue them and do some additional identifications, you just get this pair of pants type geometry, where this geometry is almost everywhere Lorentzian, except here at the crotch, where there will be a delta function singularity in the curvature. So it's a sort of mild curvature singularity that you can easily deal with. Right, so that's the flat space geometry. Now, in ADS we can do something similar, but okay, we need to be a bit more careful because here we can just draw some lines and identify, and it's fine. In ADS we need to worry about having the correct extrinsic curvatures, and that's why you need this mirroring cut on the other side of the double cone. And more specifically, if we write, for instance, global ADS, if we write it like this in sort of a light cone gauge, then what I mean is that you need a cut at V0 and at minus V0. And then you glue these geometries. Then you glue these cuts together. So that's the geometry in ADS. Of course, it's not very explicit, but the cutting and gluing procedure should make it easy to see what I mean. Right. So this is again the same picture. Now, the important thing to realize is that these geometries, I'll call them crotch geometries. It's maybe a bit weird, but okay. They don't satisfy the usual equations of motion that we encounter in JT. They have a delta function, a singularity, at these points where the topology change happens, if you will, and there's a specific coefficient here. And this specific coefficient is there because what we're talking about locally is a double cover of that geometry. And so the question is, why should we ever include these type of things to begin with? Now, the answer is that we actually include them all the time, and Don has shown that, for instance, if we want to calculate the partition function z of it, we include these type of geometries all the time. So z of it, if we put the boundary conditions of periodic time on one side and we just consider one boundary, then the geometry is half of the double cone that I just showed. And it's not a solution to r plus 2 equals 0, but there's a delta function at the tip. And where A here is the horizon area and T is the temporal periodicity that I impose. Now, these type of geometries, so how would we include those in the path integral? Well, you can do that by sticking a factor 1 into the path integral in some way. For instance, you can do it in this way, and then when you write this delta function again in a slightly different, just in a Fourier basis, then you can quickly realize that you can get these type of solutions. So a bit more concretely, we write the delta function for instance, in this way. And so I have this factor, and then the one that I want you to focus on is this guy here. If we include this in the JT path integral, and we do the phi integral now, you see that the on-shell solutions are given by this geometry. So then you can calculate the partition function associated with this geometry. That's essentially a defect partition function. And so the full partition function, if you stick that back in, so this is this defect partition function, or this alpha here is that alpha. And then the fun thing here is that there's a saddle point now for alpha, and this saddle point is precisely at the location where we expected the saddle point to be for this geometry that I showed on the previous slide, so the half of the double cone. And so we can really think of this A here as the area, the horizon area, or the value of the dilaton at the horizon. And okay, this integral looks pretty bad, but you can regulate it, and it works out. One thing that I also want to mention is that this area integral is sort of like an energy integral. So in some sense, what we're doing here is fixing the area or fixing the energy, and then at the final step we do the area integral, the energy integral. Okay, so that's a way to think about this geometry, the geometric contributions to this guy, and how you can include these type of geometries, even though the original equations of motion do not allow them. It's sort of a different gauge choice, if you will. Now, for the spectral form factor, what I advocated before is that we want to think about the double cone, and we want to add these slits, or add these delta function singularities at particular points, and then identify the slits. Now, all these geometries need to be consistent with Gauss-Bonnet. That puts some constraints on what this alpha needs to be. And in particular, we want the coefficient of the delta function to be -4 pi, and not this other thing that we had for the z of it guy. So instead, we write this delta function just in a slightly different way. We put a minus 2 pi here. And then the equations of motion for phi then tell you that, so then alpha needs to be 0. That's a constraint that comes from Gauss-Bonnet. And so the geometry that you get then is really this double cover geometry that I showed in the beginning. Now, once you do that, so alpha has been, we have done a saddle point evaluation for alpha. Then there is but the position of so the area integral, the A integral has also been done using a saddle point. And so that gives you this. And then the integral over the location, so there was also an integral over the location, gives you finally a contribution like this. Now this integral over the location of that crotch or of that delta function can also be done using a saddle point, and that basically tells you that this area will be the extremal area. At least that, yeah. Right. So let me put some things now together. So these geometries that I talked about with these slits and these delta function singularities, that smells a lot like the light cone string diagrams. And in fact, you can map these double cone geometries with the slits, you can map them onto light cone gauge string diagrams and the usual Mandelstam diagrams. And so what that in practice means is that we're gauge fixing JT to a flat metric with certain conical singularities at isolated points, instead of the usual way where we fix the background metric to be hyperbolic. So this is the usual choice that we like in Euclidean signature, and it's very convenient. The ratio of determinants that we get from gauge fixing, they essentially cancel, and calculation only amounts to finding the correct Weil-Petersen volumes. And okay, that has been done, so you can just go ahead and calculate. If you do instead gauge fix to this flat, if you do this flat gauge fixing, then the moduli space integral actually becomes very simple. The measure is very simple. But the ratio of determinants is very complicated. And essentially, most of our work is trying to show that these determinants actually do not spoil this power of time. But you can actually, I won't go through the argument here, but the crucial point here is that at late times, essentially these determinants, the ratio of determinants essentially goes to 1, and there's no interesting time dependence left at late times. Now, of course, if you want to have the correct coefficient and everything, then you need to include those, but okay, we're not really after that. We just want to do like a semi-classical calculation here. Okay, so this is what I just said as well. So the moduli then are the relevant moduli for us are the locations of these slit, of the endpoints of this slit, and the radial modulus integral can be done by saddle point. So that gives you the extremal, the on-shell contribution will then be the extremal area, and so these slits basically move very close to the horizon. They're a little bit off the horizon because when we do the integral, the square root g, so the metric also degenerates at the tip, and so that causes a little repulsion from that point. So it's slightly away from the horizon. But But anyway, the important point for us is that the temporal integral now gives you a factor of t. And for each handle, it gives you, so there's 2 points, 2 of these crotches required for each handle. And so that gives you a factor of t squared for every handle that you add. So that's the t to the 2g. And the plus one, so it was originally t to the 2g plus 1. So this plus 1 comes from the, This plus 1 comes from the usual double cone choice of relative origin. Right, so if we just imagine doing the genus 1 calculation, then, so we have these slits, so we're in this gauge, in this gauge of JT where we have these conical deficits, these constrained instantons. The temporal integral of these endpoints, that gives you this TQ, including the relative rotation. And the radial direction saddle point tells you that these slits are going to move very close to the horizon. Then, of course, there's the area integral left, and this is the usual factor from the double cone. And here we have the entropic suppression. And here I converted the area integral to an energy integral. And so this is the complete answer semi-classically for this genus 1 wormhole. This question mark here is that I'm just doing semi-classic, so I don't know whatever I need to do at low energies, how to calculate these coefficients. All right, so hopefully I convinced you of the power of time. It gives you a very simple way of thinking about these powers of time that appear in the spectral form factor, the expansion of the spectral form factor. And it sort of contrasts nicely, I think, with how you would think about it in Euclidean signature. There you need to invoke some integrability structure from these Val-Petersen volumes, whereas here it seems that the Lorentzian origin is very easy. Yeah. Now, you can also think about, just our last few slides, you can also think about the two-point function. The two-point function is a similar expansion, but the coefficients will be slightly different, but you can follow the same logic, and it gives you, again, the correct scaling with these powers of time. And we had some ideas about how to do this in higher dimensions, where you wouldn't consider these slits, but you sort of generalize that to codimension 2 surfaces that wrap the horizon, and you consider some sort of identification between those on both sides of the double cone in higher dimensions. And the topological, the suppression that you get and the powers of time, they work out in the same way, except here, instead of having just the entropy at some fixed energy, you get the entropy at some fixed energy and charge, and then you want to be in a fixed charge sector to be able to make this statement. And you can also work out what this does in real-time replica wormhole calculations. For instance, when you want to calculate this mod square of these overlaps, that should be non-zero, and there's sort of a swap of the interior between the two sides that is implemented by these crotch geometries. And so you have a nice real-time interpretation of that as well, using these geometries. And that, again, agrees with the known results. All right, so that was it. Thank you.
In the spectral form factor at fixed energy, these contributions, I guess, should cancel against something.
Sorry?
Does this cancel against something? Something else?
No.
Because the spectral form factor at fixed energy should not have a T-cube piece.
No, I'm not calculating this at fixed energy. Here I'm integrating. So this is supposed to be at fixed.
Yeah,
this
but
is just in the canonical.
Suppose we fix the energy by integrating over beta with the microcanonical weighting, then that will fix the energy in the energy integral on the right side.
Yes.
I think that the result of that thing after we integrate over beta to fix the energy should be 0.
Yes, I see what you mean. Yeah, maybe that's not visible in our calculation.
Could there be another region in moduli space that cancels against this one at fixed energy, but they can combine together somehow at very low energy to give something non-zero?
Yeah, I mean, yeah, I think possibly that might be true, but yeah. Yeah, I don't know how to see that from our calculation. I don't see another part of moduli space where there's another type that would cancel this guy.
Hey, Jorrit, great talk. Is it correct that these processes of Lorentzian topology change only capture these powers of t to the 2g plus 1, or do they capture lower powers in t from a certain genus as well?
I think the full calculation would also capture other powers of t. Yeah.
So you think it fully agrees with the analytic continuation of the Euclidean topology changes? As in, if you did this calculation in real t and you did the calculation in Euclidean signature and did the analytic continuation, would you get the same thing? Or do you need extra ingredients here to get?
No, I would think you would get the same answer, but like what I was saying, these determinants, they could give you lower powers of t in principle, but yeah, to calculate those is very complicated, and we only know what they would do at late times, but at earlier times, I don't know what the answer would be. Yeah.
I see. And one more quick question. Is it correct to think about inserting these delta functions in the curvature as integrating over the metric first instead of the dilaton, or is there another way of thinking about it? Technically, if you integrate over the dilaton, you just impose that the delta function is satisfied, right? So, all right.
Well, yeah, I think, so the way I think about it is that we integrate over the dilaton, and you get this delta function where you have this r plus 2 equal to some source, and then, okay, that gives you some metric where you can work with. But you were thinking about the other way around, or?
I was just thinking that if you don't put the sources in by hand,
Yeah.
like you want to see why you have to include such geometries in the path integral. And I was just thinking that one way of maybe obtaining them is that you integrate over the metric first. You don't enforce the constraint that r plus 2 is equal to 0 because you haven't integrated over the dilaton.
Yeah.
And you include these configurations, and then you do the path integral over the dilaton or something of that sort.
Yeah, exactly. I think a variation of what you're suggesting would be indeed that you don't integrate over all values. Like you fix the dilaton at certain points in the, and then you integrate over everything except at those points. That would also result in these delta functions. Yeah, so it's sort of a different maybe you can think about it as a different contour in some way.
Any other questions? I don't see any, so let's thank Jorrit again.